So we're trying to do the first question from the electric fields worksheet. The first question is define electric field strength. If you look at the mark scheme, in the mark scheme they are just expecting the idea of force per unit force per unit positive charge. So they are giving the idea as force divided by positive charge. So when you're dividing, that means you are finding the force per unit positive charge. So though the word unit is not there, it is right because it is given as a division, as an equation. If you're going to say it as a statement, then you have to say force per unit positive charge. But that is not enough. It's also important to mention that it is the force per unit positive charge. Yes, that's okay, but along with that you should also say that it is a stationary point charge. So you have to mention unit positive stationary point charge, force per unit positive stationary point charge. Then the next question, two horizontal metal plates are 20 mm apart in a vacuum. A potential difference of 1.5 kilovolts is applied across the plates as shown in figure 4.1. A charged oil drop of mass 5 times 10 to the power minus 15 kilogram is held stationary by the electric field. On figure 4.1, draw lines to represent the electric field between the plates. So they are asking you to draw the electric field lines. Now it is mentioned in the question that the field in the question they haven't mentioned explicitly that it is a uniform electric field, but from the idea that this is a parallel plate, you should be able to understand that this is a uniform field. You should have the understanding that between parallel plates, if the voltage is kept constant, then the field is uniform. So how do we denote the uniform field? By drawing equally spaced parallel lines, and I am putting the arrow as downward. Be careful, all your lines must touch the bottom plate and top plate as well. I am drawing the lines downward because in the question the top plate is positive and the bottom plate is negative. So if you put a positive charge here, it would move downward. One of the properties of the electric field lines is that they always start at the positive and ends at the negative. Then calculate the electric field strength between the plates. So before doing any calculation, it is important to extract out the information. So first, the voltage between the plates is 1.5 kilovolts. The separation of the plates is 20 millimeter. The mass of the oil drop is 5 times 10 to the power minus 15 kilogram. So this is 20 millimeter d, that is 20 times 10 to the power minus 3 meter. And yeah, so that is That is all the data that we are given. So they are asking you to calculate the electric field strength. There are only two equations. One is E is equal to V over D. The other is E is equal to F over Q. Now neither the force nor the charge is given, so we can't use this equation. So we will go with this equation since the potential difference and the separation are given. Potential difference 1.5 times 10 to the power 3 divided by 20 times 10 to the power minus 3 meter. So this gives you an answer of 75,000 volt meter minus 1 volts per meter. Remember, if we have used this equation, then it's better to give the unit Newton per Coulomb. Of course, both are equivalent. Then the third part, calculate the charge on the drop. So they are saying a charged oil drop of mass is held stationary. So right now the question is describing the equilibrium situation. Right now the question is describing the equilibrium situation. So in the equilibrium situation, it's better to write for the charge to be stationary. F electric should be equal to the gravitational force. The F electric from the equation E is equal to F over Q. The electric force F is E times Q. The electric field times the charge. That should be equal to mass into gravitational acceleration. So charge of the oil drop is mg over E. The mass is 5 times 10 to the power minus 15. The G is 9.8. The electric field strength calculated is 75,000, which gives you charge of 6.5 times 10 to the power minus 19 coulombs. But the issue is, you would simply found, like most of you would do all these and will go to the next question, and unnecessarily you will lose 1 mark because you have to mention whether it is a positive charge or a negative charge. So for the oil drop to be stationary, you know that the field lines are in this direction. So for the oil drop to be stationary, that is to balance the weight, it should have an upward force. Now if the oil drop had a positive charge, it would experience an electric force downward in the same direction as the electric field line. So for it to have an upward force, it should have a negative charge. Okay, so you have to also mention it is minus 6.5 times 10 to the power minus 19 coulombs. If you look at the mark scheme, if you haven't mentioned the negative charge, you will be unnecessarily losing 1 mark. In the mark scheme, they haven't mentioned this like a condition, like for the charge to be stationary, but it is better you write that so that you show that you understand the equilibrium state. The potential of the upper plate is increased. Describe and explain the subsequent motion of the drops. Now, when the potential difference increases, when the potential difference of the upper plate increases, from in this calculation here, you will have a greater value for V. Now you have a greater potential difference, which means that E will be greater. The electric field strength will be greater. When you have a greater electric field strength, the force EQ, the electric force, would be greater than the F electric force would be greater than the downward gravitational force. The upward electric force would be greater than the downward gravitational force. That means that the oil drop will move upward. If you look at that question, there are two command words there: describe and explain. The description is that the oil drop will move upward. The explanation is the F electric force greater than mg. Each will score 1 mark.